Hi everyone, welcome back to Designing Servers for Scalable Internet, Part 3. Today we're going to be talking about some common issues that can arise with servers when they're hit with too much load, and how we can build servers that scale better, how we can detect scale issues, and in general, how servers are monitored for scale issues. To start with, we're looking at pretty much the same two example files as we had in part 2. We have a client and a server written in Node.js. The server is unchanged. We have one endpoint called /login, and all it does is check if the client sent a request with a username David and a password pass, and if they did, they get a message back that says welcome in. Otherwise, they say, incorrect username and password. Our client on the left here looks almost identical. The only thing we've done is we moved the code we had last time into a function. So we now have this function definition called send request. And instead of hard coding the port, we now supply the port through a parameter in the function. So down here we call this function. But internally it's all the same. It sends a object with a username and a password to the server and then prints out a response. A client got back message from the server, or whatever the server sent to it. So let's just confirm that everything's still working from last time. So we start up our server on port 3000, and we run our client. And the server's happy with us. We supplied the right username and password, and we get a message that says welcome in. So far we have just what we had last time. Now, today's talk is really about issues with servers and what can arise if they get too many requests from clients. In general, what do we mean when we say issues with servers? Well, like any program, a server is reliant on its underlying system's resources. So like any other program, it uses CPU, it uses memory, and if it runs out of those resources, it starts to face issues. So people who design servers and run them, they are always looking at the CPU usage and the memory usage of their servers, and they know they need to fix things if perhaps the CPU utilization gets too high. But ultimately, what happens if your CPU gets too high or if you run out of memory is that the server starts to take longer and longer to respond to requests. So one metric that's particularly important with servers is what's called response time. So the response time is if the client starts a timer as soon as it sends the request, how long is the client waiting for the server to get back to them? And the reason that this is important is that human beings can start to tell. So if you load a website, maybe that website loads in 10 milliseconds or 15 milliseconds, and you think to your eyes it looks like it loads instantly. But if it takes 200 milliseconds or 500 milliseconds, your eye can tell and you feel like the page is loading slowly. So there's a constant battle when you design servers, particularly as the server gets more complex, of keeping response time low. If your response time jumps from 10 to 12 milliseconds, maybe no one will notice and you can get away with it. But if it gets too high, the users, the clients of the server start to notice. And that's when you start to get problems. So the metric that we're really going to be looking at today is this response time. And we're going to essentially monitor the response time. We're going to make it worse by making the server do extra work and having the server spend a lot of time thinking and thinking. And then we're going to go over one or two ways that we can bring the response time back down. So these are solutions for scaling servers. But to begin with, we need to monitor the response time. So the way we can do that in Node.js with this request library that we're using is in this options object that we pass to request, we're going to ask it to record the time it takes for us. So we pass a new flag called time, and we say time equals true. So we're saying, hey, this library that does the request for us, please keep track of the time. And now, rather than printing the message that we get back from the server, we're going to print the response time. So the client's going to send a request, and as soon as it gets a response, it's going to say, client got back response after X amount of milliseconds. Now, this is going to give us how long it takes for this one request to go out to the server and come back to us. So let's see what happens when we run this. So on the server side, we see the same thing. As usual, it says, the client gave me this data. But now on the client side, we see client got back response after 17 milliseconds. And if we keep running this, it'll vary a little bit, but we can say, well, right now with this one client sending responses, it's averaging about, let's say, 18 milliseconds. And 18 milliseconds is really fast. Your eye, if it took 18 milliseconds to load a web page, your eye would not be able to tell the difference between 18 or 20 or 25. But now we have a way of monitoring how much time the server is taking to get back to us. Now, in order to make things more interesting, let's have the server take more time. So let's say we're doing important work here. Maybe we're making another request to another server in this server. We're looking things up in a database. Server endpoints can start to take a bit of time. And the way we're going to just simulate that for our example is by making the server do a bit of math. So we're going to do some fake work just to waste time. So let's say we have a number, and for no reason at all, we're going to do a bunch of math. So we're going to loop, a million times. We're going to say this sum is sum times I modulo sum. It really doesn't matter. We're not going to be using this value. This is just to waste some time. And what we're expecting is that we're going to see this response time to all of a sudden shoot up because now the server takes more time and the client has to sit around waiting for longer. So let's see, let's restart the server and let's run the client. So now instead of 20 milliseconds, we get 200 milliseconds. And if we keep running this, we'll see that this is now consistently taking an order of magnitude longer. If tomorrow we need to update this endpoint and someone wants to add even more stuff, maybe this number will get even higher. But 200 milliseconds, let's say we're still okay with that. Now, the danger in having high response times is that clients come and go, and your server may be helping more than one client at the same time, serving more than one request at the same time. So let's say instead of having this one client, let's say we send a whole bunch of requests. So let's make things even worse. Let's say we're going to send 20 requests every time we run this file. So now every time we run client.js, we're going to send 20 requests to the server. And now let's see what happens to our response times. So here are 20 requests are going through, and what we can see is that the response times continuously grow. So the first request we send comes back after 200 milliseconds, but then by the time we get to our 20th request, it's taking 3.5 seconds. And now 3.5 seconds, you can definitely tell, the human eye can definitely tell that that's a long time. Now, why is this happening? Why is it that it's consistently growing? Well, as it turns out, our server here, at least in Node.js, can only handle one request at one time. So the first request is sent out, and the server starts dealing with that request, and then it gets a second request. And that second request is actually queued. The server says, wait, hold on a second, I'm still dealing with someone else. As soon as the server finishes with the first request, it moves on to the second one. So even though it looks like this one server is serving 20 client requests all at the same time, in reality, at least in Node.js, it's not truly parallel. The subsequent requests, if they come in too fast, they're queued and they have to wait a little bit for the guy in front of them to finish. So we can see by the time the 20th request comes, it's waiting quite a while. And so now if you were designing the server, you might think that this is a problem. What if tomorrow 100 people try to use the server at the same time? It's going to get way too long, too high of a response time. So what can we do about this? There are a couple ways that people try to design servers a little bit better. That we say that we like to build servers that are more scalable to a higher number of clients. And there's two ways we're going to be looking at today. One is called vertical scaling, and one is called horizontal scaling. Now, vertical scaling is essentially taking a look at the underlying system resources and just increasing them. So if you have this server running on a computer with 2 CPU cores and 2 gigs of RAM, maybe you go out and you buy a faster computer. You get a computer with 4 cores and 16 gigs of RAM. And if you run the server on that faster computer, then well, maybe this math doesn't take so long. Maybe the computer can calculate all this faster, and all of a sudden you'll see faster response times, and you'll think that that's great. That is a legitimate way of speeding up servers, of scaling servers. That's called vertical scaling, when you replace the underlying system resources with just more powerful resources, so the server has more to work with. The other way, and the way we're going to be looking at more in depth today, is called horizontal scaling. Now, horizontal scaling, the idea there is instead of increasing the resources of your one server, that instead we're going to make multiple copies of our server. And even if the amount of resources per server will stay the same, but we'll have multiple copies. And when a client request comes in, we will randomly send it forward that request to one of our copies. So it's essentially, instead of having one server running, maybe you have 3 identical ones, and they're all dealing with the same set of clients. And so the idea there is that you essentially have created parallelization. So now instead of the second and the third client request having to wait for the first guy to finish, if you have 3 servers, you can handle 3 requests truly in parallel. And that's also a perfectly legitimate way of bringing response times down, and that is a way of scaling servers. The reason that horizontal scaling is often preferred to vertical scaling is that there is a side benefit to horizontal scaling that is really nice, and that benefit is redundancy. So the idea is that if you have 3 copies of your server, and they're all serving client requests, and all of a sudden one of them dies, there's a bug and something crashes, you still have 2 copies of your server running, and your clients might not even notice because all of their requests will just start being forwarded to the 2 servers that are still running. And in the meantime, you can get the third one working again and then restore all 3. In vertical scaling, however, that doesn't work. If you replace your server with a much beefier server, well, you still only got 1. So if that one server still crashes because of a bug, you're out of luck. Your clients say, hey, your site isn't working, your app isn't working, your server is down. So horizontal scaling is often preferred for this reason. Redundancy is very nice to have in servers. It helps the system maintain a healthy state, maintain uptime. Even if stuff breaks, users will often not notice. So in our example, how can we use horizontal scaling to maybe lower these response time from 3.5 seconds to maybe something a little bit more reasonable? And the one way we can do that is, like we said, have multiple copies of our server. So what do we need to do? Well, if we're going to have multiple copies of our server, they all need to have their own port number. So rather than hard coding this port number, let's say we're going to supply the port number on the command line. So that when we start up our server, we can start up let's start with 2 copies of our server. And we're going to start one of them. We're going to supply port 3000. We see that the server is listening on port 3000. On the other one, we're going to supply, let's see, we're going to supply port 3001. So now we have 2 servers. And what we want is for our client to randomly send its requests, sometimes to the server on 3000, sometimes to the server on 3001. So the way we can do that is, well, instead of always talking to port 3000 over here on the left, let's instead have a list of the different servers we can talk to, and we're going to randomly choose one. And we can do that with the help of this library that will randomly sample one of the ports from this list of ports. And then when we send the request, we're going to use that random port. So in theory, half the time we're going to send a request to 3000, half the time we're going to send a request to 3001. And now when we run this client 20 times, on average 10 of them will come to here, 10 of them will come to 3001. The server's still going to print out client gave me blah, 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 and it's going to return welcome in. But now we're going to be interested in whether the response times have gone down for the client. So let's run our client and see what happens. So now instead of 3.5 seconds, we've got our client response down to 2.5 seconds. And if we run it again, let's get some more samples. Now it's 2.2 seconds. We run it again. We can see that it's definitely lower than when there was just one server serving requests. And we can see that this continues. If we make another server, and this it run, we're going to have it run on port 3002. And over here on the client, we're going to say, well, now let's also consider sending some requests to 3002. At the bottom left, if we run our client again, we get an even lower response time. We brought it all the way down to 1.5 seconds from 3.5. Just by adding more copies of the server and spreading the load between the servers. The word for that, logically, is often called load balancing. So we are balancing the load from the clients among our set of servers. In a real system, this would be set up a little bit differently. So rather than the client changing which servers it talks to, in between this client and the server, there'd be another entity called a load balancer. The client would send its requests to that one load balancer, and then the load balancer would forward the client's request to all of the different servers. So rather than the client having to muck around with ports, all of that's taken care of in this hidden layer in the middle. The client thinks it's talking to one server, the load balancer, but in reality, behind the load balancer, there may be a dozen servers all helping to answer clients' requests. And we can see just by this example that horizontal scaling is a really effective way of bringing down response times. Certainly, vertical scaling also works, but like we mentioned, horizontal scaling has side benefits that are really helpful to maintaining a healthy system. So this has been a brief introduction into some of the issues that can come up with building servers, particularly as they get more complex, as they start needing more time to do their work. And we've looked at two ways of scaling servers, vertical scaling and horizontal scaling. And we talked about, how can you tell when a server is struggling? So we talked about monitoring CPU and RAM usage, and also monitoring the response times. So how long the client has to sit around waiting for the server to get back to them. That's all for part 3. In part 4, we're going to summarize what we've learned, and we're going to take a look at everything that we discussed, and there's going to be a short quiz for you guys to check out and maybe test your own understanding of what we've gone over. Thanks so much for listening to part 3. See you guys in part 4.